Guys, we are back. I'm finally doing a new video series on AlphaFold 3. If you're new to the channel, welcome, I'm Killian Menton. And if you're coming back, welcome back. Sorry it took me so long. Now, as the title suggests, in this video I want to go through the process of doing a full implementation of AlphaFold 3 from scratch in Pytorch. What I think is important to stress here is that this is not about me doing the implementation, but it's mostly about teaching you how to do the implementation yourself. So in the videos, I'll kind of explain the theory about AlphaFold 3 to you, and then you can hop over to my GitHub repository where I've got tutorial code that will walk you through doing the full implementation yourself, with checks to see if you did it right. Before starting the series, I was a bit skeptical if it's really so beneficial to do a new one on AlphaFold 3, given that I already did one on AlphaFold 2 and it's kind of both protein structure prediction. But looking at the code now, I think there are tons of new things that you can learn in AlphaFold 3 new that you didn't do in AlphaFold 2. And actually there's kind of little overlap between what you need to do for AlphaFold 2 and AlphaFold 3. I want to structure this video series in 5 parts. The first is feature extraction, then we do input embedding. In the third part we'll implement the Evo former, then the fourth part is on diffusion, and fifth I want to talk about how to train AlphaFold. I know the last point sounds a bit delusional, given that training something like AlphaFold 3 is ridiculously expensive for an individual. So I want to stress here, we aren't going to train AlphaFold 3 to state-of-the-art levels. Basically what I want to do is to get to a point where we can be reasonably sure that if we had enough compute, we could have trained AlphaFold 3. What I think is cool about this structure is that each of the chapters has some pretty cool techniques you can learn within that are generally interesting for ML in general and in bio specifically. In feature extraction, we'll see how we can use the new AtomWorks framework from the Baker Lab to do feature extraction efficiently, and as an easy connection point to the PDB. In input embedding, aside of the AlphaFold 3 specific code, you can learn working with the flex attention framework in Pytorch, and how to work with block masks for computing sparse attention on sequences that are too long for full attention. In the third chapter, the Evo former, we'll implement the main trunk of AlphaFold, and we will practice using some GPU memory profiling to optimize our Pytorch code. Diffusion is likely to be my favorite chapter. Diffusion is so dominant for ML right now in regard to generating continuous output, such as the positions of atoms in AlphaFold. And I think understanding diffusion well is key to being able to design models for a lot of tasks. We'll be going through the theory and implementation of EDM-style diffusion, which is the one used in AlphaFold. And we'll also do distributed cloud training of an image diffusion model to practice for the last chapter, training AlphaFold. At the time I'm recording this, I'm not through with testing how well this works, so I don't want to make too big promises. What I definitely want to do here is implementing AlphaFold's loss function and being able to overfit a small dataset. However, I read on the GitHub of LEGO Bioscience's AlphaFold implementation that training actually converges quite fast to reasonable accuracy. And if we could actually do that, that would be amazing, I think. So, I hope you are as hyped about implementing AlphaFold 3 as I am. As a quick warning, I think doing AlphaFold 3 might be a bit more difficult than my previous series on AlphaFold 2, meaning that the videos will be a bit more fast-paced and there are some technical aspects you'll need to implement. I'm not saying that to discourage you. I think even if you haven't got a lot of experience with machine learning yet, you can just pick up a lot along the way. But just so you know, it will be a bit more difficult. And if you don't feel so familiar with Pytorch yet, you could also try the first 3 videos of my old series on AlphaFold 2. These are not specific to AlphaFold 2, these are just basics of tensors in Pytorch, machine learning, and attention mechanisms. So that's everything I wanted to say, and now I want to use the rest of this video to show you how to set up the code on your own machine to get you started for the next videos. So I'll switch to my laptop. Okay, hi again, I'm on my computer now, and I'll quickly show you how to do the setup. This will take a bit, so I think you won't be able to remember all the steps. I suggest you just follow along. So maybe pause the video, open up your own programs, and then we'll start. I set up a new fake GitHub account today, so I hope that everything will be the same for me as it is for you. Now with my fake GitHub account, I'll quickly give myself a fake star, and then we can start. So on the GitHub repository, here are the setup instructions. And we'll start with the first step that's specific to Windows users. So for Windows users, I suggest you install the Windows Subsystem for Linux, or WSL. I've got a Windows VM set up here, and I quickly show you how that works. The first thing you want to do is install the WSL extension in Visual Studio Code, and after you have that installed, you'll find when you press F1, then you can search for the command WSL, connect to WSL, and when you enter that, it will say here the Windows subsystem for Linux is not detected if you don't have installed, and you can just press install now to install it. So I'll navigate across the dialog, and it will do the download. Now, Windows Subsystem for Linux is basically two parts. First, you install the Windows Subsystem for Linux, and then you actually install the distribution. Sometimes it will do both at once, sometimes it will do only one of them, and you might need to restart either Visual Studio Code or at least, or rather like your whole machine, or at least Visual Studio Code after the installation. So we'll see about that, and I'll show you when this is finished. Okay, everything worked for me. Now I need to set up a user account in it. I'll just put in my username and a password. And with that, the Windows Subsystem for Linux is installed for me. Again, maybe for you, it would have required another step that it just installed WSL, and then you do again connect to WSL, and there would be another pop-up here. This one is just because I didn't close VS Code. So I quickly do that, restart it. And after that, we should be able to connect to WSL. Yes, this is working. So as you can see in the bottom left, it's opening the remote. And after it's done, you'll see that it says WSL Ubuntu here. And now if you open up a terminal, you can see that you are actually in a Ubuntu Linux terminal. So after this, you'll be able to follow along with the commands that I'm using for my Mac or that you'll use for Linux, because they're basically the same. Okay, so this is how the WSL works, and after that I'll go on with the other instructions. The first thing you want to do is install Git DevTools and the Package Manager UV, either by executing the Mac OS commands or the Linux commands. So for me on my Mac, I'm gonna execute these, copy them over, and go to Visual Studio Code, and this is open in my desktop folder. I'll do everything relative to that, and I'll just paste the commands. For me, they are already installed, so this might be a bit quicker for me than it is for you. And after everything works, I'll go on with the next step. And this is set up SSH access to GitHub. Now, you don't technically need this. You could also just do a regular git clone here, and for that you don't need to have SSH access. But I suggest you set up SSH access, and that's mostly because we might want to work from remote machines in the future, and mostly in the tutorials on image diffusion or like diffusion, and the one on training AlphaFold, because there we'll need access to your GitHub repository from another remote machine. And for that, it's practical to have SSH access to GitHub. So now in this terminal, I'm going to execute SSH keygen to generate the SSH keys. I'll quickly put down the file path. So I'll name the first one ID GitHub. I'll create no passphrase, and the second one I'll create for accessing cloud machines, and for that I'll put the name users Killian Menton / ID Vast AI, because that's the service that I want to use. I'll put no passphrase again, and then I can access the public GitHub key that I just created. It's important that you put .pub here and don't actually upload your private key. So your public key should look something like that. I'll quickly copy that. And then on GitHub, I'll go over to my user account, click on settings, and then go to SSH and GPT keys. There I can put a new SSH key, put an authentication key, not a signing key, and name this MacBook key, and paste the key. So with that, we basically have access from GitHub side. We just need to load the key into our SSH keychain. The command for that is ssh add, and then the name of the file you created. So for me like this. And with this, we should be able to authenticate in GitHub. You can run this command to quickly check if it's working. And if it is, this should output, hi, your username, you've successfully authenticated, but GitHub does not provide shell access. So with that, we've got set up our SSH keys and can now go on with the tutorial. I quickly go back to the repository, Now, the next thing we want to do is to fork this repository. I'm not saying that because I want to have good fork statistics. I think this is really beneficial for you because if you fork it, that means that you can do your own version control through GitHub. And this is really practical in the end when you want to shuffle code from your local machine to a cloud instance where you want to do training, because then you can just commit, push to GitHub, and then pull it on the remote machine. So what you want to do is fork this repository, then clone it. So I'll quickly click on fork here, create a fork on my own account, not Killian Menden. And here, now I can clone it from my fork. So I suggest you use the SSH link here, because with SSH, you can directly use the SSH key you just created and linked with GitHub to do the authentication, so that GitHub knows you are allowed to do pushes to this repository. So I'll copy this URL, go over here, and I'll clone this into my desktop folder. You can put it wherever you want. So git clone and then the URL. Now it's downloading the files, and I'll open this AlphaFold 3 decoded file or folder that's new here. So open folder, and then I go to desktop and AlphaFold 3 decoded. So with this, we are basically all set. This is how the whole structure of the repository looks like. So we've got the data folder here, which currently has an almost empty params folder, because of course I'm not allowed to distribute the AlphaFold 3 params to you. And then the fold inputs, where you have fold input in the format that AlphaFold 3 uses to predict protein structures. So for example, this would predict the structure of a protein with the sequence here, and this MSA, and with a ligand also in the structure of the CCD code NDG. So this is the data folder. You don't need to worry about that too much. Scripts are some utility scripts. The most important one for you is generate test results. We'll run that in a moment to generate the test results for your solutions. Then solutions is actually the full implementation that I did. So you can look here if you don't manage to implement anything and see how it's done. So this is the full code, and the corresponding tutorials folder is basically a copy of the solutions folder where the segments that you're supposed to implement, so basically everything, is just deleted out and there's only the skeletons remaining. So now here, the first thing we want to do is actually install the dependencies. So I'm going to open up a terminal and then enter uv sync to download everything. uv, you installed in the steps before. This might take a bit longer for you because you don't have all this cached on your machine. I do, because I did uv sync really recently already. So now, what you do next is to set up some Visual Studio Code settings so you can actually use this project. And the first thing you want to do is to select the Python interpreter that you just created through uv sync. So you want to select this one that is at .venv/bin/python. That's the interpreter you just created. So after you selected this, you can see that it shows up here. And if you open a new terminal now, you should see like, actually it doesn't, yeah, now it's done. So this automatically loads the interpreter and you can check which Python that is actually the one that is in the virtual environment. So with that, we did the first step. The second setting that we want to change is in the actual Visual Studio Code settings. And this is the Jupyter notebook file root. Oh, I already said this, apparently, but you need to change this to tutorials. Otherwise, the imports won't work correctly for you, because the Visual Studio Code, or the way I structured the project, is that everything thinks that it's relative to tutorials, but since you open this folder in Visual Studio Code, it won't work correctly with the imports, because the relative paths are different. So set this to tutorials, make sure you've got the extensions for Python and for Jupyter installed, and from there we're basically good to go. One thing you still need to do is generate the test outputs. This is basically in the tutorials folder. When you do the implementation, you'll implement the code, and then you need to check if you did it correctly. And the way this is done is by first running the corresponding script in the solutions folder, which already has the solutions filled out, generating the outputs that should occur in the tutorials, and then comparing it to that. So I've got a script here, the script generate test results, that actually does the running the script in the solutions folder. So we can just call Python scripts /generate test results. Then we'll select one because we want to do it for the first chapter, feature extraction. And now this runs the script in the solutions folder and generates the test outputs. This can take a moment. And after it finished, you'll see that it created the desired test outputs. So while this is running, I'll already go over to the next step, which is looking at what you would do in the tutorials folder. So all your code is going to be written in this tutorials folder. So you'll go over to tutorials, and then you go to feature extraction for the first chapter, and then to feature extraction.ipynb. I was a bit concerned because this took so long. I think it should be faster done the second way, but as you can see, all of the tests are correctly created. So now, in this Jupyter Notebook, it tells you a lot of things that you already heard from the video. So there's a lot of text explaining how feature extraction works in AlphaFold. We'll quickly select the kernel that we just created. So select the right Python interpreter, and now we are good to go. So you need to basically execute the first two cells. The first one, it's important to check that this path here is actually the path to the tutorials folder, because otherwise the imports will probably not work. If this is not here, or at least if it's not in the Python path in total, that probably means that you forgot to, in the settings, put the Jupyter Notebook file root and set it to the tutorials folder. So the second cell here is just basic setup. And after that is executed, we can go to the first cell where you need to actually do something, which is this one. So here it says to warm up, we'll start by implementing a few utility functions. Afterward, we're going through token features, reference features, and MSA features in that order. Now, head over to common/utils.py to implement the functions pad to shape, round down to, and masked mean. Afterward, run the following cell to test your implementation. We can quickly check what happens if we run the cell before doing the implementation. You can see we've got a scary error here. Non-type object has no attribute numpy, which kind of makes sense, where our outputs to the methods are currently none. So it makes sense that this will fail. So I'll show you how to implement one of them. I'll show you how to implement pad to shape. I hope this isn't too much of a spoiler to you, but I think it's good to see how coding here works. And I think there's plenty of other exercises that you can try without me showing you what to do. So I'll quickly implement this, maybe to read what it does. So pad to shape pads a data array of any shape to a specialized or to a specified padded shape using a special padding value. Here are some tips which are good to read because I think this is not trivial to implement it. So it says, implement the padding. In the output, the data should be in the top left corner of the padded array. I do that to say that padding, some people think that when you say padding, you mean put it into the middle, like you would pad an image by adding border. But here we just want it in the top left, so in the leading part of the dimensions. Now this one is the thing you might not know yet how to do it. You can create the padded array using torch.fill and then fill in the value by creating an index of the form slice, going from 0 to the dimension 1 of the data, dimension 2 of the data, and so on. This is just kind of a neat trick to fill an array or create an index for an array that you don't know the size of. The other thing you can see here is that it's probably a bad idea to have inline completions running because it's already telling you what to do. I don't want this. I'm going to delete this, and I'll disable inline suggestions real quick, which I suggest you do too. And now we can implement it ourselves. So I'll quickly do it and write padded is equal to torch.fill of the shape padded shape and with the fill value. So now I'll create the index. The index should be a tuple going up to the dimensions for dim in data.shape. So for each of the dimensions, we'll basically create a slice index. This is equivalent to having an index of the form like dim1, dim2, dim3 for an arbitrary number of dimensions. So this is how you'd create an index dynamically. And with this, we can fill in the padded values. So padded at index should be equal to data. I made a small mistake here. Maybe you can see already what's the mistake. I'm doing that on purpose so I can show you how it would like and how you would debug if you did a mistake. So now I can over here again and re-execute the cell. And we can see what happens now. Okay, it doesn't give the error instantly again. Now it says comparison failed for value pad to shape. The maximum absolute difference is 0.979, and the maximum relative difference is 1 or 100%. And the first 10 differing indices are these ones. So at location 01, there's a difference, at index 02, at index 03. So basically it seems like there's an error everywhere. And of course, what we want to look now into is how we can fix this error. Debugging is, of course, an art. My usual tactic is to just look at the code long enough until I see what's going wrong. But this isn't always helpful. I want to show you how I'd go through debugging this. And this is basically by not using this notebook, which might seem a little odd that I've given you a Jupyter notebook, but I don't want you to debug there. I think if it's working correctly, or if you can easily find the change, you can just continue doing it here. But I think debugging is actually easier when you do it through the Python debugging interpreter. And to be able to do that, I make copies of all of the notebooks that are in the tutorials and convert them to Python files and put these into this converted notebooks folder. So this file here, feature extraction notebook, is an automatically generated identical copy of this notebook, which just has the difference that this one is a Python file, so we can execute it with a Python debugger. You can kind of debug these as well, but this is never working for me, so I like doing it like this. So now I'll quickly create a debugging configuration to do that. So I'll create a launch.json file, Python debugger, and this is maybe a bit special. This is not the standard setting. I set this to debug a module. I'll put the module name, which is converted notebooks dot feature extraction notebook. So the module name basically just mirrors the path because this module here is in tutorials, our relative tutorials is in converted notebooks / feature extraction notebook.py, and the module name mirrors that. The other change we want to do here is to set the current working directory to the workspace folder / tutorials. So this is maybe kind of special, or like you haven't seen it before like this, but this is basically the equivalent of what we did before when we changed the Jupyter file root to the tutorials folder. So now with this set, we've got a debugging configuration. I'll give it a quick name, feature extraction debugging. You'll need to create a different one when you're working on the different chapters. So for the one on input embedding, you will need to create a separate configuration because this specifically calls the feature extraction notebook. But with this set, we can basically start the debugger. This will not be super helpful now because the debugger will just go through the code. There isn't an error message there. We just print out some debugging text. But I think there's one specific breakpoint that can be really helpful and it might be a bit hidden. I like to put a breakpoint into tensortrace.py, which is not a file that you'll implement. This is just some helper code that I implemented for myself to check whether your code is correct. So basically all that tensortrace does is having some utility functions to store tensors in the solutions file and then load them in the tutorials file and compare them. And you could argue that to do that, it's kind of too long. Maybe it's a bit over-engineered. But in this file, you can look for the method compare. And here in def compare, I like to put a breakpoint right here, which is where the output in the Jupyter notebook, here, it says comparison failed for test value pad to shape. And this is exactly from here, comparison failed for test value. So now with this breakpoint correctly set up, I can go over to my debug configuration and execute it. And now, because we get into this failure case where the comparison fails, the debugger should stop exactly at this breakpoint and we can inspect the values. So we'll wait for a short moment for it to reach that. And now it's stopped here. We can go to the debug console and we can inspect the values, which is v1 and v2. v1 is the value that your method generated, or in this case, my method, and v2 is the ground truth value. And as you can see, there seems to be a pattern here. So it should be 1.76, but it is 1.0, or it should be 0.4, and it actually is 0. So maybe think for a moment what could have gone wrong here. What might be a bit misleading is that this is shown as a float tensor because of the interconversion in this compare method. Yeah, maybe I'm swallowing too much. But in this utils method, like what we can guess what's going wrong here is that this is actually truncating the values here. And the reason for that is that this padded tensor here is actually currently an int tensor because that's the default value for torch.full. And it doesn't have the correct d-type. So what I'm going to do here real quick is to carry over the d-type of data and also the device of data. If you read the text here carefully, then you could have seen that it also tells you that you should do this, but of course sometimes you skip over something like that, and then you run into an error. So with this, I hope if I repeat it, we shouldn't get the same error again. We can wait for a moment. We'll definitely get a different error because of course we didn't implement all of the things we wanted to. Yeah, so we can see we got a different one, but as you can see in the output, pad to shape tests passed. Like, if it works correctly, we could also see this here. So I can quickly execute the cell as well. Oh, wait a minute. I'll restart this. Session got invalid. And if I now execute this cell, yes, it says as well, the pad to shape test passed. But now we've got an error converting a test value in round down to. So we've got an error in the different method that we didn't implement so far. And I guess that's okay because we didn't do it. So that's everything I wanted to show you for the basic setup and how to work on the tutorials file. But I want to do one more thing now, and that is to show you how you could actually use cloud computing and rent a remote GPU. For cloud computing, obviously there's a multitude of different vendors and different platforms that you can use to do it. I'm just going to show it to you with one specifically, which is Vast AI. I'm not affiliated with them, it's just the one I currently like to use because it is quite cheap. So in Vast, I'm quickly going to go over to the console. The first thing that you need to do here is to log in and add some credit. So to do a GPU here costs about 40 cents an hour. So if you wanted to do just testing, you could just put $1 here and you'd be able to do it for 2 hours or something. So you need to add some credit here. And after that, you'll want to add your SSH key so that you can SSH into the machines. As you remember, when we created one for GitHub, I already created another one for Vast AI. So I'm quickly gonna look what the public key of that was. Like this. And copy the public key over. So copy this, go over to Vast, and add the SSH key here. Save it, and with this we'll have SSH access into the instances that we are creating. Next, we actually need to create an instance, and for that you need to select a template here. I like to select the NVIDIA CUDA template from Vast AI, which works pretty well for me. And then you can put some filter settings here. The most relevant for me is the GPUs having low price, which is currently at 66 cents for me, the filter. Depending on what you put there, you'll have different options here. And then you can select the GPU that you want to use. I'm going to pick the one here. Things you might want to look out for is the model of the GPU, how much VRAM it has, and I like to look at the internet upload and download speeds as well. So I'll click rent here, and after that it will show up in your instances tab. It will take a few seconds to start running. This greatly varies. So sometimes this takes only 30 seconds, sometimes this takes 3 or 4 minutes to start. Just be aware of that. Sometimes for me also it just doesn't work. So if it's not running after 3 or 4 minutes, I usually just dump it and spin up another instance in search. So we'll wait for it. Okay, for me it loaded now after 34 seconds. And what you want to do now is to copy the IP and the port over to your SSH config. So I just copied the IP, and then I'm gonna go to VS Code and execute remote SSH connect to host, and then configure SSH hosts. So here I already wrote some text up, so I don't forget what to put. The name here is just any choice you like, which is how you'll name the instance. Then here at host name, you put the IP address. Forward agent should be yes. Forward agent yes means that you forward your SSH keys from your local SSH agent to the remote one. That doesn't mean that the remote agent and the remote machine has got access to all of your private keys. It just means they can use them to, for example, make pushes to GitHub. So the other thing you want to copy over is the port. By the way, this was here under the Open Terminal access where you can see the port and the IP. So I'll copy the port over and put it here. The other options should be user root, and identity file should be the name of the private key that you created in the beginning. So with this set, we can go connect to host, connect to Vast AI, and this new window will open up that will load VS Code on the remote machine. Now, the first thing you'll probably want to do on the remote machine is also install the Python extension there, so that execution of Python code works well. And after that, we basically just repeat the setup we did before, copy over the code from your repository. Here specifically, you want to use the SSH link, because like that, you can actually make pushes and commits to your repository on GitHub. So copy the SSH link, then go here, git clone, and then the link. And after this is cloned, you can open the folder and have your project ready. So I'm going to open /workspace/AlphaFold3 decoded, which is where I cloned it to. And now what you need to do here to finalize your setup is to do the UV sync again. You don't actually need to install all of the programs you did before, because they are already pre-installed. All you need to do is run UV sync, and then your environment will be set up. So what's cool about setting up the SSH keys the way we did is that now if we actually make a change here, for example, in the tutorials.config.py, I might make a change such that every time it gets imported, it says, "Hi, I got imported." And now this is a local change on the remote machine. This doesn't exist on your own machine. It's just on the remote machine. But now if I get a terminal again after this completed, I can actually commit this change and push it to the remote GitHub repository. So before you do that, you can quickly check that your SSH to GitHub is actually working. So you can put again SSH git at github.com. And like before, this should say, "Hi, your username, you've successfully authenticated." And with this now, you can actually make the commit. So I'll quickly add the file. I'll make sure that it is added. Then I'll do a commit. This will ask me to put some information. So I'll put my mail into the config. Not my actually one. This is the fake email I just created today. I hope you won't be able to guess my real email from it. And also my name. And with this, I can do the commit. And then after I commit it, I can push to the remote repository. This will get through. And as we can see in GitHub now, after I refresh, is that actually the tutorials folder says first commit now, because the config.py file was changed by that commit. So that's how SSH access from remote machines works. Now the second thing that we want for them is the graphic cards to work. So it's a good idea to check that as well. And so the first thing we want to do is source the Python environment that we just created. You can also do the select interpreter thing in VS Code again. So venv.bin/activate. And after the environment is loaded and we are starting a Python interactive shell, we should be able to import torch and then check that torch.cuda.is available. And this outputs true, which means that the graphics card is accessible and our remote machine is all set up. So this was everything I wanted to do in this video. I hope the setup worked for you as well. Sorry that the lighting in my room got a bit poor throughout the way. I didn't think I'd take that long. That's everything from me for today. In the next video, you'll see how to implement the feature extraction pipeline in AlphaFold. So I'll see you back for that, and goodbye.